this is about the joint work from Parsi and me. For those of you who have been at the workshop 2 years ago, 2017, they know the previous work, and actually this is an adaptation of that work, which we composed for this workshop. So I'll shortly walk you through the agenda. First, I will give an introduction to feature selection in general. Then I will go to the fuzzy similarity and entropy feature selection algorithm, FSAE, or as Parsi usually mentions, we should have named it SAFE. Would have been probably more, easier to remember. Then we will go to which modifications we did to that algorithm in order to improve it. We will show some artificial examples where we highlight what the differences are. Then we also made some small real-world examples, or not made, but we used the algorithm on some real-world examples. In this case, only 3, but we will later make some additional examples, of course. And then we will come to a conclusion and the future possible work in this area. So first I will talk a little bit about feature selection, because this is the area that we're talking about here, or that is the context of this work. So in general, we have nowadays often a wealth of information available, meaning we, for instance, have information on a lot of variables. We had some examples here before. For instance, we had a topic about crowdfunding, where we have potentially a lot of variables, so a lot of features, as we usually refer to in our context, and it might not be known which ones of those are actually relevant for the task. So for instance, if you want to do regression or classification, then usually that it's most effective to use those features that are actually relevant for the class label. So others might be irrelevant, and that actually comes with some disadvantages. So using more features, and including features that are irrelevant, of course, increases the computational complexity. It makes it harder actually to find the signal in the data, because the other features, of course, make it harder. So it makes it harder to actually find what is the pattern in the data. You can imagine if you try to find the optimal solution, it's much harder for you when there are millions of options than if there are only thousands of options, for instance. And of course, as a direct consequence, usually when you use a classification algorithm and you try to find a good solution, the more features you have, the harder it is to find the optimal solution. And if you don't find it, usually you will have a deterioration in the performance of your algorithm. Or in plain terms, you will be not as accurate as you could be. And that's why, especially for more complex problems in high-dimensional space, so with many features and potentially also many samples or observations, it's even more important to basically concentrate on those relevant features. And that's why dimensionality reduction techniques, or DR techniques, are used. And one of those techniques is actually the feature selection. So we have dimensionality reduction techniques here, and they're usually differentiated into feature selection and feature extraction, with the main difference that in feature selection we use a subset of existing features. So basically from the existing variables that we have, we cherry pick the best ones. And what are the best ones, of course, depends on some kind of measure. In feature extraction, most common example would be PCA, so principal component analysis. You usually want to generate a subset of new features. So you generate your new features, your new principal components, for instance, and then cherry pick or take those that explain, for instance, most of the variance in the data. That's the main difference between those two. And for completeness, we also have here the feature transformation, because feature extraction belongs to the feature transformation methods that do some form of transformation to the data. And there exists feature construction, but this is not a dimensionality reduction technique, because you usually keep the existing features and create additional ones to extract as much information from data as possible. So you will have a bigger set of features than the original one. That's why this is not dimensionality reduction, but it's related. Okay, and we will focus on feature selection, more specifically on supervised feature selection, because we do it in the context of classification. So in the context of supervised learning, which is classification or regression, but our focus will be on classification. There's, of course, the unsupervised one, which is usually related to clustering, so unsupervised learning, and we have semi-supervised or semi-unsupervised, where you have part of the data with some class label and others not. Well, we always have the class label, some kind of class. For instance, if you have medical data, you can imagine you know the patient is sick or healthy, and you have certain information that describes the patient, like the age and symptoms and so on, and you try to predict what are the factors that lead to a person being sick or not. And with feature selection, for instance, you would filter out those variables that are actually important. Okay. I will shortly go over our existing research in that field before I go on the adjustment that we made to the FSAE. So the starting point, which I already mentioned, is the FSAE algorithm, which is a heuristic filter method. So heuristic in that regard that it does not guarantee to find the optimal solution. There are methods that guarantee the optimal solution, but as you can imagine, those usually take quite a long time because they go through all or almost all of the possible combinations of features and then determine which is the best feature subset. While this method does not do it, as many do, or many do not, in order to find a good subset. It doesn't necessarily needs to be the optimal one, but it's usually not a bad one. And it's a filter method because we apply it before the actual classifier. So it's basically a pre-processing step that we do at the beginning to the data in order to narrow it down to a feature subset that has lower dimensionality, and then use it with the classification algorithm afterwards. So the classification algorithm is not involved before. This method was an improvement of the method from Professor Basiluca from 2011 that was using similarity and entropy, and we basically added on a scaling factor to adjust for the distance between the ideal vectors. I will come to that in a moment, a little bit more detailed. But the main idea was to use class and feature-specific scaling factors to account for the difference between the class representatives as well. Because there's some weaknesses that, or vulnerabilities that the algorithm had for certain data structures that we tried to overcome. And last but not least, we should mention that it's a univariate approach. Univariate in that regard that we evaluate each feature by itself, so uni as one, so basically the evaluation of each feature separately. So we do not account for any dependencies between the features. We just focus on how the feature is related or its characteristics are done in order to predict the class label well. Then one other approach that we took, which is more recent, is we developed another algorithm that is a multivariate method, so that actually accounts for the conditional dependencies between the features. It's also a heuristic method, and in this case we use clustering and Mahalanobis distances. Of course, both approaches have their merits and their disadvantages, and that is obvious, I guess. So the univariate approach, of course, it evaluates the feature just by itself, which can be seen as a disadvantage if in the data there are dependencies between the variables or features. But on the other hand, if they are not present or they are not strong, then it still will work very well. And also it's a rather fast approach, while most multivariate approaches are rather slow in comparison, or at least slower, which will impact a lot if you have then very high dimensional data. Okay, this is what we did, but we will focus on the first approach now. And I will go right into the algorithm, and so that we can then see what are the differences, and also because, of course, we have not all day long. So basically, the basic idea is that in the first step, after we normalize the data into the unit interval, so between 0 and 1, we would calculate so-called ideal vectors, which are class representatives. This can be done, for instance, with a generalized mean. So you can imagine if m is equal 1, it's simply the mean, the arithmetic mean. This would be one possibility to calculate the class representative. So basically, if you have a class of data in multidimensional space, you would use one data point in order to characterize that class. One can argue whether that is sufficient. Actually, in the other approach, we extend this kind of framework, but it's more computationally heavy in order to find multiple points that represent the class well. But we have one, per class, we have one ideal vector that represents that class. Then, in the second step, we calculate the similarities of the observations. So x are the observations for each feature is d, with the ideal vector, the corresponding one. So you get a similarity value for each variable value, for each observation, with the corresponding ideal vector element for that feature. So you can imagine, for instance, if you have the age, and I talk now in non-normalized terms. If you have, for instance, the age, and the mean age is 55, and then you have another age like 60, then you would say, okay, x would be the 60, this would be the 50. But of course it's normalized because it needs to be within 0, 1, and similarity will also be. And you do that with each feature. So in the end, you will get all the similarity values for each class I and each feature D, and you sum them over all the observations so that you have entropies that are specific to the feature and the class. And actually, I don't know why, but in the apparently in this PDF document, the formula went down, so that part belongs there. That is strange, to be honest, but okay. You will see it later. But the main idea is that we also have a scaling factor. But before I go into that, let's shortly have a look of what the entropy functions look like and what's the whole idea behind it. So this is an example of 3 different entropy functions. Of course, there are more, but those are the ones that we were in between using. There is the De Luca and Termini entropy from the paper from 1972, and we have from Farkas et al. They have 2 different entropy measures. But what they have in common is that for inputs close to 0 and close to 1, you get the lowest entropy values of 0, and the more you get into the medium range, closer to 0.5, the higher is the entropy. The idea in general of this algorithm is that basically you see 0 and 1 as very clear assignments for observations. So if an observation has a similarity of 0 to a class or of 1, that is a very clear decision. Either very clearly is similar or very dissimilar. While similarities of around 0.5 would be ambivalent. You are not sure, does it actually really belong there or not? And that is one of the main underlying ideas. So that's why we measure the similarities of the observation to the ideal vectors and then basically use the entropy. And if we have a lot of 0s and 1s on average, we will on average get a low summed entropy value. And on the other way around, of course, vice versa, if we have a lot of values 0.5 or close, then of course we'll get a high entropy value. So basically then we sum them, but the main adjustment that we made in the FSAE, so the previous version, was that we introduced the scaling factor, which unfortunately in the formula was jumping down. I'm sorry for that. But the basic idea of the scaling factor, I go shortly 2 slides back, even though it's hard to see because this should be there, is that we just measure the distance between each ideal vector to the other ideal vectors of other classes and average that by n-1. That is the basic idea. So we basically have as the scaling factor the average distance between a class representative to the other class representatives, a scaling factor. Why do we have this? So we have entropy, where high entropy means that the feature is not good because many similarity values are close to 0.5. And the scaling factor, which was 1 minus the average distance, basically either leaves it the same way, meaning it's the same level of informativeness, or decreases that if actually the class ideal vectors are far from each other. And I could go a little bit more into detail in that, but I think that would go out of the scope of the presentation. But the basic idea is really that this is a correction factor for the level of informativeness, of informativity of a feature. So if the ideal vectors are far from each other, you would assume that is a good sign, so you would decrease the entropy value. While if they are at the same level or very close, you would basically leave the entropy value as it is and say, okay, there is no improvement of the level of informativity. And then, of course, based on the logic that high entropy is not positive, you would order them in increasing order, so lowest entropy first, and would say the feature with the lowest entropy is the best one, with the second lowest is the second best, and so on. And then, of course, you could decide how many features you want to take. We don't have a clear threshold value, but of course you could see it in relation to each other if you want, or as in PCA, you could, for instance, try and just say I take the 5 best features or 5 best principal components. Okay, and here's just a visualization of the whole idea. We did that in order to better then illustrate what are the changes that we made. So the basic idea is you have here the observations with 2 features. You can imagine this might be, for instance, the age of a patient, and this might be, for instance, if the patient shows a certain symptom in medical terms. And then here you have the class label. For instance, the first observation belongs to the first class, the second to the second, the third to the first, and so on. Then you can calculate the ideal vectors that would be here. In this case, for instance, it could be the mean because we exemplified it with a generalized mean. Then you would calculate the similarity between all those observations with all those ideal vectors, and you would get this kind of matrix. And you see it's bigger because you have for each class the similarity. 3 class representatives to all observations makes a size of 3 times the observations, times the features. And then basically you would calculate the entropy and you aggregate it. You remember that was the sum over the observation. So basically put it in the entropy function, each of those, and then squeeze it together to have those values, and then multiply it with the corresponding class and feature specific scaling factors. Class and feature specific because for each class and feature you have one separate one. And then you aggregate it, have for each feature the score, and then you would basically rank it and, for instance, would take away the second feature, for instance, because it has a higher entropy value. So this is just a visualization of how this could work, or how this actually does work. And now the question is, which adjustments did we make? So the modified algorithm in the beginning remains the same, so you can also calculate the ideal vector, for instance, with a generalized mean or Bonferroni mean or OWA operator. And one change appears in the second step. You see it here before that we have for each, for the observations, we calculate the similarity with each of the classes. This now changes. We only measure the similarity with the own ideal vectors class. So an observation, you take an observation and only compare it to the representative of its own class. I will later at the artificial example can shortly go into why we do that, but again, it's a time-consuming thing to explain it in detail. But the basic change is that we only consider it within the class, so only for the class that the observation belongs to. And then we have an adjustment of the scaling factor, which before was just basically the average Minkowski distance. And now we do not just take the difference between the ideal vectors. So for each class, with any other class that is not the same class, so class 1 is compared to class 2 and 3, for instance, class 2 to 1 and 3, and so on. And we basically scale it, so we normalize it by the standard deviation in that class. Because the simple logic behind it is, of course, if two ideal vectors are far from each other, that's a good sign. But if the variation in the data is large, then it doesn't have to mean much. While if the variation is small, that actually is an indication that that for this feature, the ability to separate the classes is good. And then we have 1 divided by that, because in the end, if this would be high, you want to have a low multiplication factor for the entropy because you want to decrease it. Entropy should be decreased if there's an increase in informativity, or should be kept the same or even increased in case that is not the case. Okay, and here basically the same, just I highlighted it red because we have the change in the scaling factor from the previous formula, but this is the same logic, and then again we ordered in an increasing fashion. Still, the lowest scaled entropy is the best, or signals that it's the best feature. And then shortly just the changes. So we see here now we have a smaller matrix because instead of comparing each observation here with each ideal vector, so 3 of them, you just compare the first one with the first class's ideal vector. That's why it's this medium gray. Then the second one is second class. You compare it to the second classes. That's why you have a lighter gray, and so on. So we basically, the size of the matrix is decreased. This is not the main reason why we did it, but this is the effect of this. And on the other hand, we have the change here, but there's no visual change because we have still class and feature-specific scaling factors, but the factors are calculated in a different way. So this is the 2 positions where we see the change. Here we see it actively, and here I just highlighted for you so that you see, okay, there's what, where, I almost said the magic happens, but where the changes happen. And then the idea is very similar to basically aggregate it on feature level and then decide which features to take. Okay, then we had some simple artificial examples where we could highlight the deficiency of the existing algorithms. And actually we, or vulnerabilities is maybe a nicer term, where we highlight the original approach from Luca and its improvement of using this group, so class-specific similarities. And then we take also the FSAE and the change of the class-specific similarities and the scaling factor. So we also show for the original approach, so 2 approaches back, how that improvement will actually affect the results. So those are very simple examples, but they are made as simple as possible, but still capable of making our point. So in the first case, basically the logic is the following. You see the first feature, so in this direction, the first dimension. So this is the first dimension, but we can look at it from here and say, okay, the representative of, for instance, the red class will be somewhere here at 0.5, right? For the blue class as well, and for the green class, it will be the same. The problem is that the similarity of the red points with the red ideal vector will be close to 0 in most cases, or not so big. Maximum of 0.5, which is bad, but only few observations are that big. But what you might also see from here is that the similarity of the red points, just from the first feature perspective, to the ideal vector of the blue class and the green class is the same. So it's also close to 0, because the representative is also close at 0.5 on the x-axis. So what we will end up with is that all the similarities to the own class's ideal vector are small, but to the competing ideal vectors also. And this will, of course, because it's small value, either close to 0 or close to 1, will lead to low entropy values. This will be an indication of a good feature. But obviously, the first perspective here, the first feature is not good to differentiate the classes. Because if I tell you the value is, for instance, 0.3, you still cannot tell to which class it belongs. It's equally probable in this case. It's not clearly defined. So that is why the first algorithm has this problem, because it just focused on the similarity values to the own class ideal vector and the competing one. If you change that from the original one to the one that focuses on the classes, you don't have that problem anymore. Why do you have that problem not anymore? If you look at this perspective, there are many values close to 0, but some are also larger. From 0.5, for instance, to 0.2, 0.3 similarities already will lead to quite high entropy and some higher values. If you look from this feature perspective, you will have just very small ones in general. So this feature becomes way worse. Then we have the comparison of the original FSAE. Since we take into account the difference between the class ideal vectors, we also have rather clear decision, because you can imagine the representative in this direction are all close to 0.5, so there is no difference between the class ideal vectors. While in this perspective, you have one close to 0, one close to 0.5, one close to 1, so the average distance will be somewhere close to 0.5. That's why we make here the right decision, even though we have that problem with the similarities to the competing ideal vector. If we then make the adjustment of just considering for the red classes the comparison with the red class representative and for the blue with the blue and so on, and include the new scaling factor, we get a much clearer decision. So it's a very clear decision. Of course, you could argue that this is a very simple example, and indeed it is. But it still makes the point that actually this improvement will help. But we have, of course, the two other examples as well, where you can see the same development and the same way that the result is quite intuitive. So here we have basically more variance in this direction, and of course in this direction a little bit less because of the scaling, and we have only partial overlap in this dimension, while no overlap in this. So still, the second feature obviously is the best one, because if you just focus on the second feature and I tell you, for instance, 0.1, you directly know, okay, it has to be the red one. Or it should be the red one unless this is an outlier. But if I would tell you here it's 0.4, for instance, 0.4 could be red or could be blue. So it's not so clear anymore. But still the original algorithm, so the very original algorithm would make the wrong decision. The adjusted one will actually find the right way because of the difference in variance. There's a lot less variance in the data here, so the similarities will be in a much smaller range in this direction than this one. The FSAE also will do it correctly because of the difference in the class's ideal vector. So here is a bit of difference, but this difference is much larger on average. And the new one will make a much more distinct decision because it also accounts for the variance. So this difference here is maybe not much smaller than this difference in this direction, but here the variance is much bigger. So we decrease basically, we have a smaller scaling factor than in this case where we have a big difference and only a small amount of variance here and here. And that's why the decision is more clear. And then we have a very, very specific example, but it still makes is helpful to make the point, because even though it looks like a strange example, if you look at it, you can easily determine which feature is the best one, right? You can easily see the first feature is bad, because if I'm here, it could be red or green, and if I'm here, it could be basically anything. And here it could be still red and green. Well, from this perspective, it's basically almost non-overlapping when you don't count this point and those two. So, but the original algorithm, we're not surprised, makes the mistake because of the similarity values. The adjusted one, just looking at the similarities, doesn't make that mistake anymore, because, of course, this one is much more variance than in this direction. Here it's the other way around, but still this one has more smaller variation than this one, because this ranges from 0 to 1. This only from 0.1 to 0.5, so much more shrunk together. The original FSAE would have actually made that mistake here, because you have here the point. Those points are basically all at the same position. Here is a difference, but since the similarity is so strong on this regard, you will make the wrong decision to 2. But the adjusted one will actually very clearly find and make the right decision, based on the fact of the variation, that here actually on the first dimension is a lot of variation and the difference is very small, while in this regard the variation is moderate, but the difference in the ideal vectors is much larger. So we see that for those 3 artificial examples, we can clearly see that the new algorithm can actually help and make more intuitive decisions and give a more intuitive rating and basically importance rating. But of course you will say, okay, this is just artificial. Let's go into some real-world cases. We have done so far only 3 because of the limited time, but we will do some more. But yeah, here are the examples. I hope you can see them. Your main focus should be on the red line and the red dotted line and the blue line and the blue dotted line. The full red and full blue lines are the original algorithms from Luca and the FSAE, while the dotted lines are the improved versions. And you see that you see certain distinct things, and some examples is more clear than in others. If we start at this example, you see that, for instance, if you first look at the red lines, because it's the first versions of the algorithm, you see that both are initially comparable, while then the red one drops off here. It's a little bit covered by the legend, but it's down here and goes down, while the other one remains longer at the upper level before it actually decreases. Here it's a little bit going down before, but it recovers itself. So in general, it seems it makes slightly better decisions than the original one. Then we have the blue one, where we have the more clear improvement. We stay up much longer, while the other one deteriorates much earlier. Here we have the picture vice versa, where we have the red one actually goes down very early, while the other one keeps itself quite long at the upper part. But you also see that the blue one, the new one, is slightly better than the other feature selection, the original one. And here actually you see that the original one decreases here towards the end rather fast, while the new one would stay at the top, staying consistently at the 85% accuracy. And with the other one, you only see slight differences. Just a short comment to that. So this is the average performance with the feature subset used with a single support vector machine with radial basis function, k-nearest neighbor classifier with 10 neighbors, and a decision tree with minimum leaf size of 10. And then I'll already come to the conclusion. So as you've seen, the main changes that we did, or the 2 changes that we did, was to use the scaling factor in a normalized way by using also the standard deviation in the data. And of course considering similarities only to the own class's ideal vector. Then that we got much clearer and always correct decisions by determining the variable importance and which feature should be discarded on the artificial cases. And we also saw that for the real world cases we could improve on average the feature ranking. Sometimes more, sometimes less, and sometimes it was not that clear, but there is a clear tendency. And future work, of course, might include some extensions of that. We currently have it as a univariate method. Maybe we can find a way, an efficient, not too complex way, to extend it to be a multivariate method that can take into account the conditional dependencies between the variables. Yeah. Thank you very much for your attention.